All right, last time we were going over our sheet on quantum mechanics, and we discussed the principal quantum number. And you guys have that sheet in front of you. Principal quantum number is given the letter what? N. What are the values of N? 1 to infinity. And what does N tell us about? The size of the atom. And last time when we did that, did I have y'all draw orbits around the nucleus on your paper? Okay. N tells us about the size. Then we discussed number 2, the angular momentum quantum number. And yes, the angular momentum quantum number. And what's the letter designation for the angular momentum? It's the cursive L. What are the values of L? 0 up to n minus 1. Okay? What does L tell you about? It tells you about the shape of the orbital. Did we discuss that the numbers of L have corresponding letters? Did we go over that on your sheet? Okay, it's on your sheet, but it says that if L is equal to 0, that corresponds to a letter of S. If L is 1, that corresponds to a letter of P. 2 corresponds to D. And 3 corresponds to F. Okay? Theoretically, it can go higher than that, but where we are right now with the elements that we know, it does not go any higher than that. Okay? But from there, it would just pick up with the alphabet. Okay? I'm going to talk more about angular momentum quantum number, but before I do, I'm going to draw. What am I drawing, y'all? My Pictionary team.
Staircase.
Keep going. That's not it.
A swimming pool. The table.
The periodic table. Jack's on my team. Okay. Yeah. The periodic table is what I'm drawing. Now.
Castle.
Castle. See, no, it's periodic table. That's what's on the card. Okay. You were late. Like the right answer's already been given. That's okay. These are the period numbers going down the left-hand side of the periodic table. Those are your principal quantum numbers. Okay? Now, the periodic table is also divided by the angular momentum quantum numbers. The first 2 columns, these are S. And what we just said, that if it's an S, that corresponds to an L is equal to 0. Helium up there at the top right is also included in that. That's an S. All of these over here, those are your p orbitals. P orbitals correspond to an L is equal to 1. What are the transition metals in the middle? This is S, this is P. Those are your d orbitals. That corresponds to L equals 2. And then those elements at the bottom, those rather rare elements that we hardly ever use, those are your F orbitals, and that corresponds to L equals 3. And so sometimes in reading in your textbook or reading on Alex, it'll say things like the D block elements. Do y'all see now what that's talking about? It might say the F block elements, etc. Now, what does this mean, this angular momentum quantum number? We said the angular momentum quantum number tells us the shape of an orbital. S orbitals, it's on your handout there, your quantum mechanics handout. S orbitals, y'all, have a spherical shape. Do you see on your handout, I've drawn I copied and pasted a picture of a 1s orbital. And do you see how that shape, it comes about by just a whole bunch of dots, right? There's just dots that were made over and over and over. And it's a probability density graph. So where the concentration of the dots ends up, it tells you the shape of an orbital. An s orbital, we describe that as a sphere, because it's got to be 3 dimensions. What's an orbital? if you have an electron in a 1s orbital, that means that electron, I'm going to do it with my hands with a sphere, that means that electron is moving around somewhere in this sphere. We don't know if it's going around and around or it's zigzagging, but it's moving around in that sphere. This would be a 1s orbital. What would I have to do with my hands to change this 1s orbital to look like a 2s orbital? I would make it bigger because the 2 is telling you the size. So see, an electron in a 2s orbital, it's still moving around in a sphere, but it's got a larger space to move around in. Likewise, 3s, 4s, etc. Okay?
So with the principal quantum number, like it can only be within those certain regions, like, right? Like it can be a sort of like a fine border.
Okay, it's, the principal quantum number tells you the size of the area where the electron is. A bigger number is a larger area it can be in. And so that's a good question. Can it only be in that border? No, but the highest probability is that it's in that border. Okay,
So we're just theorizing as it.
we're theorizing that that's where you're most likely going to find it.
I'm not gonna lie.
Okay, remember the Heisenberg uncertainty principle says you can't know exactly where it is or where it's going, so we can theorize. Now, a p orbital is shown on your sheet there. A p orbital, y'all, we refer to that as a dumbbell shape. And then I was going to attempt to take a picture. Please be in my library. Yeah. This is a picture from your book of p orbitals. This one's showing the probability density, and this one's showing you what they look like, and so we call them dumbbells. So if an electron is in a p orbital, that means that it's moving around somewhere in this area. And so here's an analogy that I heard one time, and it helped me, so I'm going to tell y'all, and it kind of hits on what you're asking too. Y'all, if we took 2 Coke bottles and we put them mouth to mouth, do you see that those Coke bottles would kind of take this shape? Okay, those Coke bottles represent a p orbital. Now, we're going to put a fly in the Coke bottles. The fly represents the electrons. The electron, singular, okay? And what we're going to do is I'm going to sit those Coke bottles right here on the front desk with the fly in them, and then imagine we all leave the room. And then we're outside, and we have a discussion outside, and we say, okay, y'all, where in that room, where do you think the fly is? Well, we know the shape of the room, don't we? And we know where we left the fly. And so we would say that fly is somewhere in this area in that room. Do you see how that tells us where it's most likely going to be? Is there a chance that the fly has escaped the Coke bottles? Yeah, there's a chance, small chance. But the highest probability of where the fly is still in the Coke bottles. Okay, and that's what orbitals are. It tells us the highest probability of where the electron's going to be found. And so that's a p orbital. And then a d orbital, again, this is just a picture from your book. This is the shape of a d orbital. We call it, y'all, clover leaf. Do you see how this one, I don't know if y'all can see it good enough, that's a clover leaf. These are clover leaves. This one right here is a different one, because what are these? These are when you graph the solutions to the Schrodinger's equation. This is what it gives you. Okay, so if an electron's in a d orbital, it's moving around somewhere in that space. Okay? Now, n. N is the principal quantum number. N can be anything from 1 to infinity. This is what was there, okay? I'm just keeping it all here, Olivia. N can be 1, 2, 3, 4, 5, 6, 7. Where is N on the periodic table? It's the period on the left side, okay? What's the value of L? We said, I'm going to jump screens here. We said N can be from 1 to infinity. L can be anything from 0 up to N minus 1. So, if N is 1, L can only be 0. Because L is 0 up to n minus 1. If n is 2, what can L be? 0 or 1. If n is 3, move that one up a little, what can L be? 0, 1, and 2. If n is 4, what can L be? 0, 1, 2, 3. Catch the trend? Okay. Now, just to remind ourselves, if L is 0, that corresponds to an s orbital, doesn't it? If L is 1, that corresponds to a p orbital. If L is 2, that corresponds to a d orbital. And if L is 3, that corresponds to an f orbital. Okay? Next quantum number. The third quantum number is called what? Magnetic quantum number?
Can you go back to that last thing for a second?
Yes. Oops. Okay.
Yes.
Magnetic quantum number. What it like principal quantum numbers N, angular momentum quantum numbers L. What's the magnetic quantum numbers letter thing? ML? What does it say ML can be? It looks, I need to tell you. Do y'all see under number 3 it says A, can have a range from? Do y'all see that? Y'all, what that says is it can be from L, from negative L to positive L. It looks like -1 to +1, but it's my font. Negative L to positive L, including 0. So that's the values it can be. What does it tell you about the electron orbital? It tells you the orientation of the orbital in space. Bless you. Okay? We're back here. We just said that the ML depends on the L. What we learned 2 minutes ago is that the L depended on the N. If N is 1 and L is 0, then ML, it can be from negative L to positive L, including 0. Do you see that ML can only be 0? There is no negative 0. It's just 0. So on this one, if L is 0, ML can only be 0. Now we've got something different. If L is 1, then ML can be -1, 0, and +1. Because the ML is from negative to positive, including 0. Okay, so moving down to the next one. If N is 3 and L is 0, ML can only be 0. If L is 1, ML is -1, 0, and +1. If L is 2, then ML is -2, -1, 0, +1, and +2. Okay, and I'm going to finish these out. Because I ran out of room. This little table I'm making is also, hang on, in your book on page 281. It's table 6.2. Okay, but now you see where it all comes from with this table. Okay, let's elaborate on what an ML is. We just wrote that the ML tells you the orientation of the orbital in space, okay? If the orbital shape has an L equal to 0, that means an S orbital. That means a sphere. Y'all, a sphere in space. If a sphere is rotating, can you tell? I mean, it's a sphere. It only has one orientation in space. Therefore, if you have an S orbital, there's only one possible value of ML. It only has one orientation in space. Okay? Now, if L is equal to 1, how many possible orientations in space are there? Yeah, it's 3. It's -1, 0, and +1. There's 3 possible orientations. So where does that come from? I'm going to jump back to those pictures I took of your book. If L is 1, that means a p orbital. That's what this is, a p orbital. 1, 2, 3 orientations. 1, 2, 3. That's why the possible values of ML are -1, 0, and +1. Okay? Here's a d orbital slide. How many possibilities are shown there? There's 5 of them. That means when you have a d orbital, you have 5 possible values for the ML. Now, from here, we did magnetic quantum number. What's the 4th quantum number? The spin quantum number. The spin quantum number is labeled MS, and it can be +1/2 or -1/2. This one's easy. There's no 0s and 2s and -1s. It's just +1/2 and -1/2. That's the only 2 possibilities for the spin quantum number. And it tells you the direction of the electron spin. That is all I'm going to say about it right now. It'll make more sense in a little bit. Okay, for now, we just need to know it's plus and minus 1/2. From these quantum numbers, we are going to write an electron orbital diagram. Have you guys looked at Alex?
I tried.
Tried? Mm-hmm. Did y'all see something that looks like a graph? Okay, here's where we're going. It's not really a graph, but an electron orbital diagram looks like this. And you have energy increasing on the y-axis. We have to write the orbitals in order from lowest energy to highest energy. You have to know the order, okay? Well, how are you going to know the order? You are going to take, I'm about to jump screens, I'm going to come back here. You're going to take this diagram, and I need you to visually overlay it on the periodic table in the room that we're all going to look at. Okay? We read the periodic table like we read a book. How do you read a book? How do you read anything? Left to right, one line at a time. On the periodic table, you go in order of atomic number. Which number is the atomic number on this one? The blue number. That's also the number of protons. That's also how the periodic table is arranged, by atomic number. So we start reading. And first, y'all, we read hydrogen and helium. According to that diagram, aren't hydrogen and helium 1s orbitals? That means our lowest energy orbital is 1s. We write that at the bottom. Hydrogen and helium are numbers 1 and 2. What number comes next? 3? Yes? Look at number 3. 3 and 4, lithium and beryllium. Do you see that those are 2s? All right, what comes after 4? 5. 5, 6, 7, 8, 9, 10. What are those? They are P's. What number P? 2P. How did I know there were 2P and y'all knew there were 2P? They're on the second period. 2P. Okay? After number 10, what do? 11 and 12. What are those? 3S. That's what comes next. 3S. After number 12, you go to numbers 13 through 18. What are those? 3P. After number 18, you go to 19 and 20. 4S. Okay? Now I call it a little glitch. What comes after 19 and 20? It's number 21, and it's numbers 21 through 30. Those are the D's, but they are 3D. What? How are those 3D? Yeah, they are on the fourth period, but they are 3Ds because the solution to Schrodinger's equation says they are 3D, not 4D. You should have to remember that. Okay? You got to do 3D all the way over to zinc, number 30. Then you get here. What's the name of this one? GA. What's that? What's that? Gallium. Number 31 through 36. You're normal now. Do you see there 4? This is the period. They're 4P. What comes after 4P? 5S. To learn, use some electron configurations. Huh? I know you didn't.
I was just genuinely curious.
No, I know you didn't. There's so much you could get from this, and this is just your foundation. This explains how things bond. It explains why some things are magnetic. I mean, quantum theory. What comes after 5S? 4D. Are y'all following me on that? What comes after 4D? 5P. I'm out of room, but I'm going to keep saying them, okay? And you can find it in your book. It does this chart in your book. Okay, what comes after 5P? 5P ends with, do y'all see 5P is right here, indium through xenon? Okay, so for number 54, we go right here to 55 and 56. Those are 6S. Okay, look at the numbers. Because we've been reading atomic numbers, and it's been fine so far. What do these numbers do? Do I go right here?
No.
Follow the numbers. What are these? 4F?
Yeah.
That's 4F. That gets me all the way through to 71. Now where do I go from there?
Big up there.
You go back up there.
5D.
5D,
Mm-hmm.
6P.
Wait, what?
After 5D, that gets us all the way to here. Then we're here.
So we went from 4F down there. Oh yeah, 'cause we're a number behind with the middle, with the D's, right?
Yes.
Okay.
Yes, yes.
All right. I'm gonna take my time with them.
5D, 6P, 7S, 5F, 6D, 7. Yes,
Yeah, what page it is?
it's in your book.
I'm just sleep on this.
Okay, this is on page, it doesn't go all the way up, but page 288.
So what it?
Page 288 shows an orbital diagram, and there's another explanation on page 291. Page 288 and 291. Okay, so this is an electron orbital diagram. We're getting to the part where it's really fun, and then y'all start seeing it come full circle, I promise. Do you see that when I write all this, 1S, 2S, 2P, 3S, yada, 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 I'm telling you the N and the L. Because the ones and the twos and the threes and the fours and the five, that's N. That's the principal quantum number. The S, well, that's L. If it says S, it means L equals 0. If it says P, it means L equals 1. If it says D, it says L equals 2. I'm about to jump screens on you in front of you. See, the letters tell you what L is. Okay? You have a question, Alex?
Yes, I don't know if I missed it, but what's the shape of the F? 'Cause-
The shape of the F orbital is beyond the scope of this textbook.
Oh, okay, so I didn't miss it.
No, you didn't miss it. And I looked them up earlier.
Yeah, it's been-
I mean, you can Google them, y'all. And I know y'all can't see very good. I'm holding up my phone. There they are. It's just a bunch of little ovals and balls and flat stuff. And it's not like dumbbells and cloverleaf. It's like, it's beyond the scope of this book. There they are. They're not beyond the scope of the book. Okay? Basically, I mean, the book says it's not going to explain them to you. All right, so that electron orbital diagram, look, it says 1s. It says 2s. It says 2p. It says 3s. It says 3p. Okay? It says all this. If it's in...
They're all orbital bodies, right?
These are quantum number solutions. Okay? I guess they could be called orbital values. Well, that's fine. Y'all, if it's an s orbital, this chart tells us that s orbitals have one possible orientation in space. That means that on our electron orbital diagram, every time we wrote s, we need to put one blank by it. There is one possible orientation in space. I am doing blanks. Your book and Alex, they're going to draw squares. Y'all, I'm just not taking the time to draw all the squares, okay? I'm just doing a dash. So, like Alex is going to have a little square here, and the book has squares. I'm just not doing it. Okay? Everywhere there's a p orbital, how many possible ml values are there on a p orbital? There's 3. That means when we have a p orbital, we need 3 blanks. How many blanks do I need on a d orbital? I need 5. Oh. I got a little errant there. Okay, so that's your electron orbital diagram. Y'all, this is what an electron orbital diagram for most of the elements look like. As a side note, I'm going to write this up here and then I'm going to erase it. Hydrogen's electron orbital diagram, remember us talking on Tuesday about how Bohr studied hydrogen and how his calculations worked for hydrogen? Okay, that's because hydrogen's electron orbital diagram, it actually looks like this. Like you got 1s, 2s, and 2p are on the same energy level. 3s and 3p and 3d are all on the same energy level. But that is only the diagram for hydrogen. For all other elements, every degenerate orbital is on its own energy level, like this. Okay. Because hydrogen only has 1 electron. So,
When we started doing this graph right here, you put hydrogen, helium, and what's helium be a P?
no, helium, hang on. So he's asking if helium's a P. Helium is still an S. Oh.
Helium always breaks rules, man.
Put graphite on my rocket book.
Oh. Do you see this, Isaac, that it's an S?
Yeah, I didn't see that before.
Okay, okay. All right, now, in this orbital diagram, we are going to fill it with electrons, y'all. And how we draw electrons in an orbital diagram, we draw them like this, half arrows. They either point up or they point down. Okay? Each blank can only hold two. Okay? So do you see that the S's can only hold two? How many can the P's hold? 6. How many can the D's hold? 10. Okay, they can only hold two. Hydrogen has how many electrons? 1. You have to start low energy. You can't just throw it in there anywhere you want. Y'all, that's what hydrogen's orbital diagram would look like. Only had 1/2 arrow to draw. I'm going to put it right there. Okay? From the electron orbital diagram, I can write what is called an electron configuration. And the electron configuration for hydrogen is 1s1. Make sense? Good, good. Why is this not- Okay. Now, working our way up, I'm going to be jumping between two screens because I'm trying to keep everything here today so it'll be recorded. I just erased that one, so I'm starting blank. How many electrons does helium have? 2. Okay, watch. 1, 2. What would this, on the next screen, what am I going to write for its electron configuration? 1s2.
Oh, never mind. The E for electron.
Yes.
I'm thinking helium. Never mind.
Okay. I'm going to start from scratch again. I know y'all can't always erase them on your sheet, but I can. Lithium. How many electrons does lithium have? If it's neutral, has 3. So look. 1, 2, 3. That's lithium's orbital diagram. What is lithium's electron configuration? 1s2, 2s1. I'll show you a shortcut later. Huh?
How do you know how many electrons it has?
Okay, like when I say lithium, how many electrons does it have? How do you know the answer's 3? Because right now we're doing neutral stuff. And lithium, I can tell from its atomic number, has 3 protons. Therefore, it must also have 3 electrons in order to be neutral.
How you get the 180?
Okay, so lithium is 1s2, 2s1.
Go back to the screen and see what she said. Oh,
Okay,
okay.
all right. Now,
The order of everything in the periodic table is going to take forever.
what do you mean, like by the order?
Well, like, instead of just like during the test, every second I'm looking up there.
That's why I'm going to give you a periodic table to have right here, so you don't have to look up there. I'll save you all that head turning, okay? I promise the more of these you do, you can get to where you don't have to look.
Take forever for me to get that down.
Yeah, we'll practice. We're going to practice. Okay, I'm going to erase this and then start over, and then I'm going to quit erasing. Boron. How many electrons does boron have? 5. So I'm going to draw them. 1, 2, 3, 4, 5. So I take this, and then on my next slide, I want to write an electron configuration. Can y'all read this and tell me what I'm going to write? 1s2, 2s2, 2p1. Okay, now, hang on, because there's some little rules I got to introduce you to. For starters, boron, guys, y'all look at the periodic table, and y'all tell me it's got 5 electrons. And this might not seem very helpful right now, but it can be helpful. Look at the superscripts. 2, 2 and 1. That adds up to be 5. And so it's kind of a little checks and balances thing, because as y'all can see what's coming. These can get really long. And you can accidentally write or skip one or something. If you'll go in and you'll look at those superscripts and add them up, you can check and say, ooh, wait a minute, I'm not adding up. Oh man, I skipped a 2p orbital. Okay, so that won't happen. Now, a couple of things we're doing here. And you will see it said in the book, you'll see it on Alex, you'll see it on the test. Aufbau principle, A-U-F-B-A-U. You are doing the Aufbau principle. When something says, use the Aufbau principle to write the electron configuration, y'all, that's the building up. Building up. In other words, maybe you're not there yet, but you're going to get there. Maybe you can look at the periodic table and you can tell that boron is a 2p1. But the Aufbau principle says that's not how we do it. We don't go and say boron's 2p1, carbon's 2p2. The Aufbau principle says we start 1s2, 2s2, 2p1. We build up to it. Okay? The other principle that you're going to have to use, and you're about to see it, you hadn't seen it yet, it's called the Pauli exclusion principle. The Pauli exclusion principle says no two electrons can have the same 4 quantum numbers. Yeah, you have seen it. Y'all, I'm going to show you a diagram here of the Pauli exclusion principle. If you had to write 2 electrons in this 2s orbital, how have we been doing that? Haven't we been doing them like that? One goes up, one goes down. The Pauli exclusion principle says that if I wrote them like this, if I wrote them both pointing in the same direction, it says that's wrong. Do you see how that fits the rule, how that violates the rule?
So what does the symbol represent? Why not just put 2 there? What does the symbol represent?
What symbol?
What are the symbols for the electrons?
The electrons? It is just conventional to use the half arrows to show that they're spinning opposite directions. Because you can't have 2 spin in the same direction in the same orbital, and it's just arrows show that really easy. That's it. Okay, so these 2 electrons right here. Do y'all see that both of them have a principal quantum number of 2? Because it says 2s. What's their L value? S. L is 0. What's their ML value? If L is 0, ML has to be 0. Okay, so at this stage, they both have the same 3 quantum numbers. Pauli exclusion principle says they've got to have 4 unique quantum numbers. Do you see that the MS for the first one is positive 1/2 and the next one is negative 1/2 because they're spinning opposite directions? Do you see that if we wrote them like this, they would both have the same 4 quantum numbers, and Pauli exclusion principle says that can't happen? Okay? I mean, you can say it on the recording if you want to. I'm going to now introduce another rule, and it's Hund's rule. And you're going to see me do it right here, so y'all watch. Let's do nitrogen here. How many electrons does nitrogen have? 7. So here we go. I'm not going to erase. I'm just going to pretend. 1, 2, 3, 4. Hund's rule says you got to do this. 5, 6, 7. Hund's rule, it's for stability. Hund's rule says that this
Just to make it a little easier.
is correct. symmetrical. It's actually for stability. Hund's rule says this is wrong. That's going to be in the p orbitals, and that's going to be in the d orbitals. Hund's rule says you work your way all the way over with one pointing up, then you go back and you point another one down. Because pointing up means you're spinning the same direction, right? They're all the spin quantum numbers, plus 1/2, plus 1/2, plus 1/2. And Hund's rule says this correct way is stable. Hund's rule says if you do this, if you go like plus 1/2, negative, or even up, down, that's unstable. It didn't happen.
Is it until you finish that row?
Yes, so what we would do, like here, we'd finish the row. If we needed to put more, now we go back and we put them going down. Okay? So that's nitrogen. Can you guys tell me the electron configuration for nitrogen?
Would it be 2p3?
It would be 2p3. 1s2, 2s2, 2p3. Okay? Now, electron configuration. Without me doing them and showing them to you, can you write the electron configuration for sulfur? Okay, we're going to do it together. Let me ask you this. Can I write the electron configuration, or do you want me to show it to you here first? Show it first? Okay. So I'm going to pick up from here. Sulfur, we got to show 16 electrons. So what have we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's the diagram. So what you wrote for an electron configuration is, tell me, 1s2, 3p4. Okay. Can you do calcium? Oh, I thought you're cold.
No, I thought that what you said.
I said I'm hot.
Oh, yeah. It's comfortable for me.
Okay.
I have a hoodie on under this. You see it?
I'm a little, yeah, I'm not.
I mean, but she's
I'm comfortable.
she's teaching. You working a lot of chemistry.
I am. I keep moving, so.
A lot of friction up there.
No, there's not a lot.
Generating heat.
Just a little bit.
Are you guys ready to read your electron configuration for calcium to me? Okay, I'm ready to write.
2s2, 2p6,
Yeah, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What you think? Not hard?
There are easier ways of writing it, yes.
There is an easier way to write it, but before we do that, I want you to appreciate the easy way. So can y'all tell me what strontium, what's the symbol for strontium? Because this is seriously how I turn it into hard on the test, is I write strontium and y'all go, oh my God, which one is that? That's not hard. Which one's strontium? Mm-hmm. Strontium's SR. You know it. What's SN? Did you say SN? No, what's SN? 10. Has anybody ever told you to learn all the elements and their symbols?
I was supposed to,
Yes, I told you that. Yes. Okay.
but I don't have a good memory.
All right, tell me what strontium is. Go ahead, Jack. I'm listening. 1s2.
2p6, 3s2,
How about 3D 10? 3D 10? That's what it is. 6, 4p6, 5s2. Okay. Whew. A shortcut would be nice. Okay, we say shortcut because it is. It's also called a noble gas configuration. Sometimes it's referred to as the condensed. Okay? Where are the noble gases? Group 18. Look at sulfur. Sulfur has 16 electrons. Agreed? What noble gas comes closest to sulfur without going over? Neon. Do you see, I'm drawing up here, that's neon right there. 1s2, 2s2, 2p6. So what you could write for sulfur, if doing the condensed version or the noble gas version, is neon 3s2, 3p4. And now sulfur, that's not real short for sulfur, but come on. It's going to help us out on strontium a lot. All right, calcium. Find it on the periodic table. What's the closest noble gas without going over? Argon. Do you see if that right there is argon? That right there that I put in brackets takes care of all 18 electrons that argon covers. Therefore, its noble gas configuration would be argon 4s2.
Could you also just say 4s2?
I'm doing the way.
You need to show the others are full.
I'm learning one.
I know, it's just a technicality. But that's why when we write the formula for table salt, couldn't you just say ClNa? It's not how you do it. You gotta say it. You see what I'm saying? It's just not how we do it. Okay. You can do whichever way you want on the test. I think Alex, when y'all get to these on Alex, it's gonna say, like, do the longhand or do shorthand. On the test, I'll let you pick which way you prefer. What's strong?
Shorthand.
Mm-hmm.
And
Underneath
it's
is
from
short.
X's for the shorthand.
I feel like it will. I feel like it'll force you to do both directions. I don't know. Hadn't looked at it in a minute. What's strontium shortcut? Yeah.
So what you determine, like, what you mean by mix or like what you looking at? What number are you looking at for you?
Well, like for strontium, strontium has 38 electrons.
Mm-hmm.
What noble gas comes closest to 38 without going over? Krypton. 36. That's how I knew what to write.
I think that was like the only difference between these two elements.
Okay? Now, we're doing good. So, what if I didn't say write the electron configuration for calcium? What if I said write the electron configuration for the calcium ion. Well, that's not the same as calcium.
I got you, okay.
What does calcium ion mean?
Is it different about electrons?
Yeah, it means it has a charge. Therefore, yes, you're right. It means it has a different number of electrons. Do y'all know what the charge of a calcium ion is? You do. You do. Don't overthink it. What's the charge of a calcium ion? Positive 2. How do you know it's plus 2? It's in group 2. So when I say calcium ion, this is what I mean. Ca with a plus 2 charge. All right? This is calcium on the left, calcium ion on the right. What has to happen to get from here to here? For something to go neutral, to become a cation, it has to lose 2 electrons. Electrons are negative. If you lose them, that's going to make a cation. So which 2 would I use? Isn't that 2 electrons right there? So if I strip those away, the electron configuration for the calcium ion is simply argon.
What about the 4?
The 4 is empty. So you don't write it. You don't write all that empty stuff.
Right, okay.
And this is to make it neutral.
This is to give it a charge. This over here on this side is neutral, but now we're writing on the charges. Okay?
And to make it have a positive charge, you take away those.
Lose electrons, it becomes a cation. Here's strontium. What's the charge of a strontium ion?
So two.
It's also plus 2, because it's also in group 2. So what would the electron configuration for the strontium ion be? Krypton. Okay, now, I got one more thing to show you. Y'all are doing great. This is sulfur. What charge will it form? -2. How would you name that? You don't say sulfur ion. How do you name the negative stuff? Sulfide. There you go. Sulfide ion. Okay? Am I still losing electrons? I'm gaining. How many? 2. Where am I going to put them? That'll hold 2 more, won't it? Okay, so what would its electron configuration be? Ne3s2, 3p6, or argon.
Is this a part of this, or do we have to do it like when we're prompted to give the charge?
You'll be told that it has a charge. And you'll,
Not leaving it neutral and make positive.
like if I say potassium ion, that means K, but if I say ion, it's got to have a +1 charge.
So if you give us like the sulfide, are we gonna get, what you doing?
Like it always has to be plus one charge?
Potassium always has to be +1. We're going back to what we learned in chapter 2, like that everything in group 1 forms a +1 charge. Everything in group 2 is +2. We're going back to that.
So you, instead of us, and I only show our work of how we got the neon with the 3s, 2, 3, 4, 6, we just write AR for that.
You don't even have to show your work. If on that one you just wrote argon, I know what you did. I mean, I trust that you knew exactly what you were doing.
Okay, cool.
Mm-hmm.